This is a presentation of an approach by a paper Optimal Action Extraction for Random Forests and Boosted Trees by Cui et al. From Washington University in St. Louis in 2015. This presentation talks about counterfactuals for classification. That is, if we have a classification task like do I sell my apartment and we don't sell it, then what is the smallest change or change combination to my apartment's features that I have to make in order for it to get sold?
That are basic, which we all
machine learning.
end up solving are
Data science tasks
regression and
that are basic,
in your credit
which we
scoring
all the
world,
time will end up
tasks are
solving are, for instance, twofold
loss given
regression and
default
classification.
And classification
In your
tasks
credit
are your
scoring
probability
world,
of default
the regression
tasks.
tasks are your loss-given default problems, and classification tasks are your probability of default tasks. The two most successful approaches of how these are getting solved in machine learning world are artificial neural networks and decision tree-based approaches. In this presentation, we talk about machine learning task classification, and we tackle it with decision tree-based approaches. So out of the four options, those two are being selected. In order to put everyone on the same page, let's see what a regression and classification tasks are like, and then proceed to a specific example. For regression, we could ask, what is the temperature outside of my apartment? And if we use a decision tree one here, to analyze this problem, our four features in question are valued at 1, 4, 5, and 6. Then this decision tree at first looks at the first feature and checks whether its value is above 2.5. And we can see that it's being 1. It's not, so the decision tree branches is to the left branch. Then it looks at the third feature and checks whether its value is above 28. And again, the value isn't about 28, so it branches to the left branch. And if we tackle the temperature regression problem with this first tree, then the regression value outputted by the tree is minus 0.009, which is the answer.
It's important
Considering the same decision tree and the same decision, it's important to see, as we were looking at features 1 and 3 here, in the space of those features. The decision tree, while it's making its decision, is doing a 90-degree cut in the first case in the feature 1, and then nextly in feature 3. And then selects the pertinent region and outputs minus 0.009 for all this region, given that our data point is here. And this is what the decision trees generally tend to do. The decision tree could be more complex, but it always does cuts like this below 2.5, below 28, above 1.2, above 26. And it always does 90-degree cuts in the space and then outputs a value. And this is a more complex tree, which this decision you can see the output value here is plus 0.009. And the decision trees with varying depths always do those 90-degree cuts. Whereas for regression, we were considering continuous values as outputs for classification. The output will be 0 or 1. We now switch with the example of the same tree to a task of classification. The feature values 1, 4, 5, 6 will be the same coincidingly. And we want to see whether this apartment, now the 1, 4, 5, 6, are apartments parameters in this problem. Whether this apartment will get sold or not. We will use a forest for that. There are 10 trees. The first tree is the same one we saw, so given the 1, 4, 5, 6, it is outputs the leaf minus 0.009, and there are 9 more trees, second, third, fourth, and so on. You can see that the trees have varying depths, so the first tree has 2 levels of branches. The third tree, only one, it considers different features, like the first tree considers first and third feature, the fourth tree second and third feature. And as we run the given apartment through those trees, we get these leaves as outputs. This is an unlucky coincidence that it always chooses for this example the first leaf, as you can see, of the tree. Doesn't have to be this way. But now let's see how the classification result will be output. We take the leaves that have been selected and we line them up and sum them up. So the sum of the circuit leaves is minus 0.207. If it was regression, this would be the answer. But for classification, what we need to do is to run this through a sigmoid function. Sigmoid function at its x-axis has this sum that we have just calculated, and at x equals 0, the sigmoid would output 0.5. So here we see that the value is just below 0. And the output will be somewhere below 0.5, 0.448, which is now where we will apply a threshold 0.5 for classification, and see that since it's below 50%, and this will be your chance of the apartment being sold, then the final result is no, the apartment will not be sold. And we will now come to the central question of this presentation, namely, since this apartment is not getting sold, what is the smallest change to the parameters of this apartment or the properties of this apartment when it comes to real life that we would have to make in order for it to get sold? This is essentially an XAI, or explainable artificial intelligence question. And let's tackle it now by crunching an integer linear programming ILP problem put forth here. We will go through this problem equation by equation, but let us at first say a few words about the little toy problem that we have solved here. This problem, while training the model, had only 3 apartments. The features were 1, 4, 5, 6 for the first apartment, with class being 0, 4, 5, 6, 7 for the second, with the class being 0. And so forth. The third apartment was the one which got sold. So this is how we trained our forest with 10 trees for this particular problem. The integer linear problem that we set up will have about 40 constraints and 40 binary variables that we'll see in detail later. However, in real-life problems there could be, for instance, for something we've looked at, 1,200 trees or so and 150 features, which means that the problem will have 40,000 constraints and 40,000 binary variables and 40 million coefficients to optimize. So it's going to take a powerful solver to crunch through it. Let's first look at the objective function of the problem, the first equation, and we notice that there are decision variables Vij, and depending on the features of the apartment, a function Cij, which creates a distance matrix based on it. Let's see how this, in a detailed way, it plays out. We have 4 features for this particular apartment, and as we look at feature 1 and the entire forest, let's note the places where feature 1 is at hand. We see that it's only in the first tree, and the value that is being looked at is 2.5 or above. So what we do now is we bin the first feature from 2.5, so the first bin will be minus infinity to 2.5 included, and the second bin will be above 2.5 to plus infinity. So this is how, for the purposes of this problem, we bin the first feature. Let's now bin the second feature. We look at the forest values which deal with the second feature, and we see that as, although it's been tackled many times, the values, if you look through all the red circles, are just at 4.5 or 22.5, which means that we bin again the second feature and just one more example, minus infinity, to 4.5 above 4.5 to 22.5 and above 22.5 to plus infinity, which gives us the free bins for the second feature. Now we do the same exercise for the third feature, and then love with similar bins. And then when we look at the full feature, it's been used just in 2 places, but it gives us also 3 different bins, from minus infinity to 6.5. Above 6.5 to 33.5, and above 33.5, so we see that we have binned the features into 11 different bins for those 4 different features. Coming back to the objective function, Bij are binary variables, pretending to those 11 bins. Let's see what Cij now is the function of XC. When we look at the objective function for the class 0, meaning that if we take our apartment, run it through the integer linear programming problem, and predict and see for class 0, meaning that what would be the changes that we would have to make in order for the class to be predicted 0, then of course we don't have to make any changes because the class already was predicted to be 0, meaning that in that case the Vij, the 0, 1 variables will select this bin here, as 0 changes are belonging to this bin. In order to give an understanding of Cij, the function of XC, we now take the final result, the counterfactual solution, jump to it right away, which says that if the class was to be 1 for our apartment, we will have to make the smallest following changes to the features of the apartment. The first feature doesn't have to be changed at all, so this is okay, and this remains in this bin safely. But the third feature has to be changed from 5 to above 5.5, and the fourth feature has to be changed from 6 to above 6.5, so there is some change that has to be made to the apartment's condition. And the second feature has to be changed the most from 4 to above 22.5. And these changes will shift the active bins to those constellations and retain the first in the current state.
Once again,
so this is the counterfactual solution and the Vij values for it. Once again, in order to understand Cj, let's now look at what the lowest limits to the changes made in order to arrive at the counterfactual solution. So the first feature didn't have to be changed. The second had to be changed by at least 18.5, meaning that from 4 to 22.5001 at least such distance has to be taken. The third by at least 0.5, and the fourth by at least 0.5. So what Cj is about is exactly this matrix of distances, meaning that, for instance, if our change to the second feature would not be from 4 to 22.5, but from 4 to 4.5, or rather 4.5001, because the bin starts from above 4.5 then. This feature would have to be changed again by 0.5 at least, or at least by more than 0.5 to be very exact. So this distance matrix is Cj, and we couple it multiplying it one by Vij, the decision matrix regarding the bins that have been on-switched for different features. Well, Vij is this matrix, Cij is this distance matrix. Let's now take turns going through the equations of the problem. The third equation depicted here just says that for Vij it's a constraint on Vij, one bin gets selected for each feature, meaning that the solution that we look at here for the final counterfactual solution already satisfies this constraint, but exactly in each column just one selected bin we will have to rely on. Next up is in the second equation phi tk. Phi tk is in the forest the question whether the kth leaf of the tree number t is turned on. So for instance, for the first tree, the first leaf is turned on. For the fourth tree, the first leaf is turned on. And it's been solved for all the trees and all the k leaves. 10 trees, 30 leaves if you count them all together. Let's now look at the equation number 5. This is solely about phi tk. It says that one leaf gets activated on each tree, meaning that if you fix a tree, t equals sine 1, and sum it over until the leaf number, which is 4, leaves, then only 1, 1, and only 1 will be selected. Let's now look at the constraint, number 1, which is the second equation. And while we look at its value, it's essentially the calculation of the forest result, meaning that it takes HTK, and HTK is the value of each leaf that is being outputted by the tree. So you can see it sums over all the trees and all the leaves. So HTK is really all the leaves outputs. It multiplies by phi tk, meaning the leaves that are being selected, meaning that since phi tk in the problem is a binary variable, as you can see, it just selects those leaves for outputs that are being outputted by the respective tree. The final weight for weighing cat boost trees as hair is equal to 1 for cat boost trees. And as we look at the output calculation, which we saw at an animated slide before, this value will have to be above z. But you notice that there is no sigmoid function in this constraint. So if sigmoid function had to be above 0.5, then this means that z perspective is 0, because for sigmoid's input above 0, the sigmoid's output would be above 0.5. Having gone over almost all the equations, we now conclude with the last, the most complex one, which ties together features, selecting each feature just one bin, and the trees of the leaves, each tree out with just one leaf. Let's look at the intuition of the topic. Let's not now look at the tree number 4. For the given counterfactual solution, the tree will look at feature number 2 and see that 22.5001 is above 4.5 and branch here. The tree will then look at the feature number 3 and see that 5.001 is not above 28, and branch here selecting leaf number 3. We have herewith given the Vij variables, explicit numbers. For feature 2v has v21, v22, and v2 free. For feature free, v has v free 1, v free 2, and v free 3. When we look at this third leaf of the fourth tree, and as this constraint evolves, it takes all the leaves of all the trees. But if we look at this particular leaf, we are going to be looking at all its ancestors, meaning the green branch and the red branch. And at each ancestor, we look at into which direction we want to go and which v variables lead to that direction. Meaning that, for instance, here for feature 2, if we want to go above 4.5, we have to select either this v22 bin or v2 free bin.
we want to
And
go.
for feature 3, if we want to be below
variables lead to
28,
that
we have to
direction.
select either this
Meaning that, for instance, here
V31
for
or
feature 2,
V32 bin.
If we want to go
You
above
see that
4.5, we
depicted
have to
here.
select either this
And if we
V22
want to go
bin
for
or
feature
V23
2 to
bin.
the other direction,
And
then
for
we have
feature
to
3,
select
if we want to be below
V21.
28, we have to select
And
either
if
this
we want to go to the other
V31
direction
or
with feature
V32
3,
bin.
we have to
see
select
that depicted
V33
here.
here. So this is where we
And
have
if
to
we want to go for
What we
feature 2
have
to
to
the other
select
direction, then
given
we have
where
to
we
select
want to go.
V21.
Remember
And if
that
we want
we're
to go
working
to
our
the
way
other direction with
backwards
feature
from the
3, we have to
solution,
select
so this is the
V33.
counterfactual solution. And we can see
So
that. We
this
really do
is
end up
where
in
we
the leaf because
have to go,
V2 free
what
here
we
and
have to select
V32 here have
given
really
where we
been
want to go.
switched on in the
Remember that we're
counterfactual
working our way
solution.
backwards from the solution.
So the
this
tree
is the
will really
counterfactual
branch
solution.
to this
And we can
leaf.
see that
But now let's look at one other
we
leaf.
really do end up in this
For
leaf
instance,
because
the first
V2
leaf
free
you see that the value
and V32
of the second feature, this
here
has to be
had
less
really
than
been switched on in the
4.5,
counterfactual solution.
leading
So the
only
tree
to
will
the
really branch
direction
to
of
this leaf. But
V21.
now let's look at
And the
one
value
other
of
leaf.
the third
For instance,
feature
the first leaf,
will have to be
you
less
see
than
that the
28,
value
which leads to the direction
of
of
the second feature
V31 and
has to be
V32
less than
here and here.
4.5,
So you see
leading
that
only to the
although the
direction of
second level
V21.
branch would branch the
And
right
the value
way,
of
the
the
first
third
level
feature will
branch
have to be less
doesn't.
than 28, which
Thus,
leads to
this
the
leaf is not
direction of
being
V31 and
outputted by this
V32
tree.
here and here.
To sum
So
the
you see
fourth
that although
constraint up,
the
we
second
see
level
that
branch
for
would
each
branch the right way,
each
the
leaf,
first level branch
the
doesn't.
tree's leaf
Thus,
is switched
this
on
leaf is not
only
being
if the
outputted by
sum
this tree.
here, which takes for each ancestor the each
To sum the fourth
respective bin
constraint
that
up,
could be
we
turned
see
on.
that for each tree's
And then
each
those
leaf,
bins that
the
are really
tree's
turned on
leaf is switched
will
on
give
only
such a
if
sum
the
that
sum
it will
here,
let the leaf be
which
turned
takes
on.
for each ancestor
The reason for
each
the
respective
division in
bin
denominator
that could
is
be
that
turned
the
on.
denominator
And
takes
then
the
those
set of
bins
all
that are really turned
ancestors,
on
here the red and
will
green,
give
and looks
such
at how many
a
there are, namely 2.
sum
And by
that
the
it will
virtue
let
that
the
each
leaf be
feature
turned on.
only has one bin switched
The
on,
reason for the division
then
in
this sum
denominator
will
is
also be
that
in
the
the numerator
denominator
will be
takes
2,
the set of all
in case
ancestors,
this leaf
here
for the
the
given
red
tree
and
is switched
green,
on. So it's
and
going to be
looks
2
at
divided
how
by
many
2,
there are,
enabling
namely
the
2.
switching on of the
And by the virtue
respectively
that
leaves.
each
In
bin
conclusion, we
only,
can
each
say
feature
that
only
the
has one
method
bin switched on,
converged in
then this
counterfactual
sum will also
solution,
be in the
whereby the
numerator
smallest change
will be
combination
2,
that one has to
in
make
case
to the
this
properties
leaf
or
for the given
features
tree
of
is
the
switched on.
apartment in
So
order
it's
for
going
it
to
to
be
get
2 divided
sold
by
was
2,
identified.
enabling the switching on of the respective.
The tree calculation was introduced as
In
a
conclusion,
constraint,
we can
which
say
meant that
that
the
the method
apartment
converged
will
on a
have to be sold.
counterfactual solution,
The
whereby the
objective
smallest
was
change combination
minimized
that
to a
one has to
value
make to the
above
properties or features of the
19.5
apartment
for
in
the
order for it to
features
get
that had
sold was
previously been
identified.
normalized
The
in
tree
such a way
calculation was
that all
introduced
the
as a
trees of
constraint,
the
which meant that
forest
the
would
apartment will
produce
have to be
an
sold.
output,
The objective was
and
minimized
all
to a
the
value above
features would have been turned on.
19.5 for the features
We're
that had previously
effectively
been
looking
normalized
for,
in
so
such
to
a way
say,
that all the
cheapest
trees of the
change
forest
to
would
the
produce an output
apartment
and all the
that
features
we
would
would
have
have
been
to
turned
make
on.
in order to
We're
reverse
effectively
the
looking for,
market's
so to say,
decision.
cheapest change to the
Anything
apartment
else would be
that
an
we would have to
overkill.
make in order
The amount
to
of
reverse the market's
combinations that
decision.
has to be
Anything
looked
else
through
would
is
be an overkill.
astronomical.
The amount of combination that has to be looked through is astronomical.